My name is Karen Daly and I teach mathematics at DKIT, a third level college in Ireland. This video was produced to further assist my first year computing students with their mathematical studies. At the end of this tutorial, you should have gained an understanding of the fundamentals of graph theory. Enjoy! Let's consider this example. A graph G is defined by the following adjacency matrix A. So A is given by this big matrix here, and the matrix has a set of ones and zeros within it. 1 means that there is a connection between two particular points. 0 means there is no connection. Part A says represent G by means of a diagram. So for this part I have to set about drawing a graph of G. Now if we look up here, you see that labeling each row A, B, C, D, E and F, and labeling each column A, B, C, D, E and F. These are actually the vertices of the graph. And what I do is I represent a vertex by a dot. So I put in a dot and I label it, and I'm going to call the first dot or vertex A. Next I go to the row A and I move along row A and I look at what A is connected to. Well, A is not connected to itself, but it's connected to B. So what I do is I draw in a vertex B and a connection or an edge between A and B. So in graph theory, this line here is called an edge. If I continue on, I see that there's a connection between A and D. So again, I need to put in vertex E and put in an edge connecting A to E. And lastly, I see A is connected to F. So I'm going to put in a vertex F and an edge connecting A to F. I repeat this process for row B. So A is connected, or B is connected to A. I already have that in, so I don't repeat that. B is connected to C is next. So C is a new vertex. I haven't got that in. I'm going to draw it here, and B is connected to C with an edge. B is connected to D. Again, D is not in, so I'm going to draw in D. Let's say we draw in D here and join it with an edge. And also B is connected to E, so we'll just do this connection here. E is already in as a vertex. Repeat the process again for C. C is connected to B. I already have that in. C is connected to D. Now D is already a vertex, so I just have to draw a line between C and D. And that's C done. Next, moving on to row D. D is connected to B, we have that in. B is connected to C, we have that in. And then D is connected to F, we haven't got that in. Now, rather than crossing over all the lines I've drawn, I'm just going to do a loop because it looks neater and easier to read, saying that there is a connection from D to F. Again, this connection is called an edge. And as I said at the start, it can be a looped line as well as a straight line. Moving on now to row E. Row E. E is connected to A, we have that. E is connected to B, we have that. And lastly, E is connected to F, we don't have that. So I'm just going to draw in that connection. And for F, F is connected to A, we have that. F is connected to D, we have that. And lastly, F is connected to E, we also have that. So that's a diagram that represents the graph G. Now let's move on to part 2. We want to represent G by means of a set definition. Now to do this, we actually need two sets. We need a set called V bracket G, which is the vertex set of G. And that gives you a set. Remember, open a curly brackets for a set. And in here, we just list all the vertices that go to form G. So the vertices are A, B, C, D, E, and lastly, F. And it's a set, so we close the brackets at the end of the set. The second set we need for this definition is the edge set. So capital E of G, so bracket G. So the edge set of G. And that's equal to, so again, open a bracket. And in here, we list all the edges. So starting at A. A is connected to B, so AB is an edge. And then I put in a comma to show that that's one edge, and the next one is AE. Put in a comma, the next edge is AF. Put in a comma to separate the elements. And now there are all the edges involving A. If I move on to B, I have B is connected to C, B is connected to D, and lastly, B is connected to E, comma. If I move on to D, D is connected to B, D is connected to C, and D is connected to F. If I move on again to E, E is connected to A, we have that. E is connected to B, we have that. But the last one we haven't got is E is connected to F. If we move on to F, F is connected to A, D, and E, and we have already listed them edges because the edge, an edge, let's say AB, is the same as the edge BA, so you don't write them down twice. So what I do then is I just close the brackets and I have the answer for a set definition of the graph G. So in conclusion, we have three separate ways in which we can define a graph. The first way was this here, the adjacency matrix. The second way was a diagram. And the third way was a set definition. And you should be familiar with all three definitions. Sorry, I just noticed there that I'm missing one of my edges, and the edge I'm missing is CD. I was so worried about running out of space at the end, I forgot that one. Right, so CD. So there are actually 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. Now let's look at part B of the question. It says identify 1, the degree of vertex B. Firstly, how you write that. In graph theory, you write that D for degree, open a bracket and put in B, right? So that's the degree of B, vertex B. And that's equal to, the degree of vertex B is the number of edges that leave B, as it were. So you can count them, 1, 2, 3, 4. So there are 4 edges that either come into B or leave B as you want to see it. So the degree of B is equal to 4. You can answer these questions from the set definition or the adjacency matrix, but it's probably easiest to answer them from the graphical representation of the graph G. So that's why I've duplicated it up here in the corner. So part 2 of the question asks you for a closed path, so we'll underline that. It's a closed path of length 5 beginning at D. So a path is just a journey that you take. It wants to begin, the path begins at D, so we'll write down D. The path will also need to end at D, so D will be the last letter I write down. The path has length 5, which means I want to move along 5 edges for my journey. Now a path can visit vertices more than once, and it can also move along any given edge more than once. So I have a lot of choices here when I want to write out a closed path of length 5 beginning at D. There are many answers to this question. One possible answer is if I move from D to F, right? So if I move from D to F, I define it like this. You just go DF. There's no commas, dashes, lines, anything between the D and F. You just write down DF, and it's understood that the first leg of your journey travels from D to F. So I've crossed over one edge then to do that. Then maybe I might move from F to A, so I just write down the letter A to say that I've taken a journey from F to A. Then maybe from A I might travel to E, right? So now I have gone through 3 lengths, right? D to F, F to A, and A to E. Maybe after E then I might visit B, right? So E to B. And after that then I might go back to D, right? Because I want length 5. So if you count them, 1, 2, 3, I'm just doing 3. And then E to B is 4, and then back to D is 5. There's my 5 lengths there, or I could put arrows on them either if I wanted to. So it's a closed path, so it starts at D, ends at D. And note also that to define a path of length 5, right, I actually have written down 1, 2, 3, 4, 5, 6 letters. Because remember, to define one path, D to F, I needed 2 letters to begin with. So that's the answer to part 2, or a possible answer for part 2. Now, part 3 asks me for a subgraph of G. Again, there are many answers to this question because a subgraph of G is just a part of the original G graph. So this is the original G graph up here, or a diagram of it, as I had in part 1 or part A. And if I just take a part of it, it doesn't matter how big or how small. I'm just going to choose A to B and maybe put in that edge. So that's a subgraph of G, and that's a diagrammatic representation of it. I could also represent that by a set definition. And the set definition would read, let's say a subgraph of G, let me say I call it H, right? So the vertex set of H is just equal to the set A comma B, and the edge set for H, which is a subgroup of G, is just equal to, there's one element in it, it's called AB. So I can give the answer like this as a diagram. I can give the answer like this as a set. And just to finish it off, let me say if I call A1 the adjacency matrix for H, it would look like this. I'd have a column for A and a column for B, a row for A and a row for B, and I just fill it out accordingly. 0, 0, and there's a connection between A and B. So that's my third way in which I could give you the solution to a subgraph of G. Probably the easiest is this one here, because a little diagram suffices and it's very simple just to draw. So just to recap, remember that the degree of a vertex is the number of edges that leave that vertex. So for the degree of B, there's 4 edges leaving that vertex. The closed path of length 5 beginning at D, so if it's closed it has to end and finish at the same letter. Make sure you don't put any commas or dashes when you're writing it down. You just list the vertices as you visit them. It's a path, so you can move along as many edges as many times as you like, or visit as many vertices as you like. It wants to be, you're asked for length 5, so remember that if it's length 5, you have 6 letters written down to define length 5. And lastly, the subgraph. A subgraph is just a portion of the original graph. And probably the easiest way to define it is this one here, part 1, where you just draw a little diagram of a portion of the original graph. You can define it using set theory or an adjacency matrix also. I just did them there so that you get a little bit of practice at seeing them again. Now let's look at part C of the question. It says, part 1, show using the adjacency matrix the number of paths of length 2 from A to E. And part 2 says, list the paths for part 1. So the number of paths of length 2 from A to E. So if I reproduce the graph for G, right, this is the graph for G, it's quite simple a task to look at the number of paths of length 2 starting at A and ending at E. So for length 2, one possible path would go from A down to F and then over to E. So I can list that, A, F, E. So that's a path of length 2 from A to E. Another possible path would be to go via B, so A to B and then down to E. So another one is A, B, E. Now there's no other path that does that, as you can see from the diagram. So there are only 2 such paths. If you had a very big network with lots of different vertices, then it wouldn't be possible to find the number of paths of a length, let's say 5, from one point to another. So part C1 gives you an opportunity to use a different method to find the number of paths of any given length from one point to another. And it's a method that uses the adjacency matrix. And to find the answer to this question, what we have to look at is we have to find, right, the entry, right, in row A, right, so it's going from A, column E of A squared. The A squared comes from the fact that the path is of length 2. So if the path was of length 3, you'd have to look at A cubed. So to get A squared, what you do is you multiply A by A. So that's A multiplied by A will give you A squared. And we want to look at the entry in row A, column E. So row A is this row here, column E is over here, so you want the entry here. Now recall the multiplication of matrices. To get that entry, what you do is you take column A, and you multiply it by the corresponding entries by column E, and you add up all the values. So if I put in these entries from my original adjacency matrix, I get A is, I should have made this a bit bigger, it's 0, 1, 0, 0, 1, 1. Okay, that's row A. And column E is 1, 1, 3 zeros and a 1. 1, 1, 3 zeros and a 1. Right? Now if I multiply the corresponding entries of this row and this column, what I'll get is it's 0 multiplied by 1 plus 1 multiplied by 1 plus 0 multiplied by 0 plus 0 multiplied by 0 plus 1 multiplied by 0 and lastly plus 1 multiplied by 1. So, and I add up all these. 0 by 1 is obviously 0, but 1 by 1 is 1. 0, 0, 0, and the last entry, 1 by 1 is 2. So it's 1 plus 1, which is equal to 2. So there are two paths of length 2 from A to E. And that's what we found in part 2 anyway. When we went to list the paths, we found there were two paths, AFE and ABE. So to recap, we can use the adjacency matrix to find paths of any length from any vertex to another vertex within our graph. Here we're asked to use the adjacency matrix to find the number of paths of length 2. If it's length 2, we have to look at the adjacency matrix to the power of 2, or A squared in this case. And we want to look at the entry from A to E is the path, so the entry is in row A, column E. To get that, we have to get A squared, you multiply A by A, you get row A, column E, you multiply the corresponding entries to get the row A, column E entry of A squared, multiply them as I've done here, and you get the value 2. You can list them very easily from the diagram version of G. The two paths are AFE and ABE. Now if we look at part D, it says state giving a reason for your answer, right? So make sure you give a reason if the graph is planar. Now, a graph is planar if you can draw the graph without any of the edges intersecting each other, right? So you can see I did that from the outset, right? There's a reproduction of my graph G. So the answer to this question is yes, G is planar, right? It is planar because, right, I can draw a diagram of G with no edges intersecting or crossing, right? And you show that diagram. So if I was to show the diagram, there it is, right? That's the diagram of G with no edges crossing over each other. And that's the answer to that. So again, just to recap, a graph is planar if you can draw the graph without any of the edges crossing each other. So in this case, we were able to do that. So yes, G is planar. Now let's look at part 2. It says, state giving a reason for your answer if the graph is Eulerian. Now, a graph is Eulerian if and only if the degree of every vertex is an even number, right? So if the degree of any one vertex is an odd number within the graph G, then the graph is not Eulerian. And so that's the case here. So what I'm going to write down then is that G is not Eulerian, right? So that's my conclusion. And why? Because the degree of, let's take a point A, right? The degree of A is equal to 3, right? And 3 is an odd number. 3 is an odd number. And as I said to you that a graph, right, a graph G is Eulerian if and only if, right, I'll write it in words, degree of every vertex of G is an even number, right? So a graph is Eulerian if and only if the degree of every vertex of the graph G is an even number. So in this case here, graph G, the degree of A is 3, because remember the degree is the number of vertices that are actually coming out from A, so or edges, sorry, coming out from A. So it's 1, 2, 3. So the degree of A is 3. That's an odd number, so obviously then it's not Eulerian. Now let's look at part 3. Part 3 says state, again, giving a reason for your answer if the graph is G is Hamiltonian or not, right? A graph G is Hamiltonian if there exists a closed path which visits each vertex once. So we want to find, is there a closed path that visits each vertex once. Okay. So if we look up here at graph G that I've drawn up here in the top right hand corner, if I start at, let's say, vertex A, it's a closed path, so I'm going to have to finish with A, right? And the path has to visit each vertex only once, okay? So let's say I start at A, and let's say I visit E first, right? So I'm going to come down here and I visit E. So I visited A, I've started at A, and I visited E, right? Then let's say I move up to B, right? So I move up to B, so now I have visited B, right? Then let's say I move down to C, across to C, so now I have visited C. Then to D, right? Moving up this path here, right? So I'm now D. Let's say I go around then to F, right? So I move around this path to F. And lastly, I'm back at A, right? So it has been possible to do. I started at A and I finished at A, so that's my closed path. And in between, I have visited each vertex only once. So I was able to find that closed path. So the answer is yes, it is Hamiltonian. Right? Because that path that I have just written down, the path A, E, B, C, D, F, A exists. And that's the answer to that question. So to recap, graph G is Hamiltonian if within that graph there is a closed path which visits each vertex once. In our case here, I was able to find that closed path beginning and ending at A, so yes, it is a Hamiltonian graph. So let's look at part E1. It says state, giving a reason for your answer, so that's important that you have to give a reason for your answer, if the following graph G is a tree or not. So to do this question, we have to understand what a tree is, right? So a tree is a connected graph with no cycles. So I'm going to look for two things. Is the graph connected, and does the graph have no cycles? So if we look at this graph here, what's the definition of connected? Well, a graph is not connected if it has two or more parts to it that are not joined to each other. You can clearly see that all the vertices in this graph here are joined within the one framework, as it were. So this particular graph, G, is connected. So it is connected, so there's no difficulty. It obeys that requirement to be a tree. Now let's look at the next one. Does G have any cycles? Now it actually does. It has more than one, in fact. So G has cycles. G has cycles. So it's not going to be a tree as a result. So let me highlight these, just one particular cycle maybe. If I name the vertices A, B, C, D, E, and F, then I can answer the question by saying that G is not, it's not a tree, right? It's not a tree because it contains a cycle, right? And I can give an example of a cycle that it contains. Let's say I take this one here, B, C, F, B. So you can see a cycle here is a route, so you go from B to C to F to B. So you follow, you start and end at the same point, and you visit two or more points on your route. So in conclusion, if you want to check if something is a tree, check firstly if it's connected, and then check are there any cycles. If both hold, then it is a tree, but if one or the other don't hold, then it's not a tree. So in our case, it's not a tree because G has at least one cycle. It has more, in fact. So if we look at part 2 then, part 2 asks us, if the graph G is not a tree, which it is not, identify two spanning trees for G. So let's look at the first spanning tree. Now, what a spanning tree is, it's going to remove some of the edges so that it transforms the graph G into a tree, and it's going to be called a spanning tree. So if we start building it, there's A, right? So if we connect A, let's say to B, right, and connect B to C, right, and connect, let's say, D to A, and connect D to E, let's say, and lastly, let's say we connect B to F, right? Now that structure there, right, is a connected graph. It contains no cycles, so it's called the spanning tree for G. So that's one possible spanning tree. There are a few different ones, so let's do another one. Let's say again we just start at A, and this time instead, let's say we connect it again to B, right? And let's say we connect B to again C, and let's connect C this time to F. Now A will have to be connected to E, right, because there's no other, or D, sorry, because there's no other connection there, but E could be connected to B like this. So there's another possible spanning tree for the graph G. So let me just recap this. G is not a tree, so to form a spanning tree for G, what you do is you remove a sufficient number of edges so that the graph remains connected but has no cycles. And that's what I did for 1 and 2. There are two possible spanning trees for G. Okay, let's look at part F. It says, given graphs G and K defined as follows. So graphs G and K are defined using a set definition. You're given the vertex set and the edge set for each graph. Show if these graphs are isomorphic. Now, isomorphic means, are they essentially the same graph? If the graphs are not isomorphic, give a reason for your answer. And if an isomorphism exists, show clearly the isomorphism. So my first task is going to be to draw both graphs. So I'm going to draw graph G here. So I've got a vertex A, and A is connected to B. You can see that in my edge set. A is connected to C, and A is connected to D. So A is connected to, let's say, C, and A is connected to D. Doesn't matter how you draw it. Okay. Continue on. A is connected to C, A is connected to D. B is connected to E, so let me bring that out here. B is connected to E. B is connected to C, so that's that connection. B is connected to D, that's that connection. And then C is connected to D, so C is connected to D. So let me just do a little loop around like that. Okay. C is connected to E, C is connected to E. And lastly, D is connected to E, so that's what I get. So that's what graph G looks like. The other graph is graph K. So graph K consists of L. So L is connected to M, right? L is connected to O, and L is connected to P. Likewise, M is connected to O, M is connected to P, and N is connected to P. So N, let me put it out there, is connected to P. N is connected to O, and N is connected to M. And lastly, O is connected to P also. Now, even just in me drawing them graphs, it's pretty obvious from my diagram that they are essentially isomorphic, because if you just look at the two diagrams, they're pretty the same. This might not always be the case. It's just turned out like that as I drew them. So what I'd suggest that you do is form a table comparing graphs G and K. And the things that you should compare in this are, let's say, the number of vertices. Look at the number of vertices of both. Look at the number of edges for both graphs. And also look at the degree of the vertices for each graph, right? So if I look at these for each of the two graphs, let me just fill that out. So the number of vertices for graph G, it's A, B, 1, 2, 3, 4, 5. There's 5 of them. There's 5 vertices. If you look at the vertices for K, there's 1, 2, 3, there's 4, there's 5. There's 5 of them as well. So they're the same or similar, so that's a good thing. Now, if they weren't the same, you would automatically conclude that G and K are not isomorphic, because obviously for the two graphs to be the same, they'd have to have the same number of vertices. Do exactly the same for the number of edges. Let's count the number of edges. 1, 2, 3, 4, 5, 6. There's 7 edges. 8, 9. Forgot them too. There's 9 edges for G. And there's likewise, counting them, 1, 2, 3, 4, 5, 6, 7, 8. There's 9 edges for K. Again, they're the same. If you found that they were not the same, again, you would conclude that the graphs are not isomorphic. Now, if I look at the degree of each vertex for G and for K, I'll need a little bit more room, so let me just push this up here a little bit and write these down. So, the degree, let me change colors, the degree of A is equal to 3, because there are 3 lines coming out from it. The degree of B is equal to 4. I'll continue this down here a little bit. The degree of C, you can see very clearly, is 4 as well. The degree of D is equal to 1, 2, 3, 4 again. And lastly, the degree of E is equal to 3. Okay. If we do the same for graph K, we find that the degree of L is equal to 3, the degree of M, the degree of N, the degree of LMNO, and the degree of P is equal to. Right? So if we look at the degree of M is 4, the degree of N is 3, the degree of O is 4, and lastly the degree of P is 4 also. Now if we compare these degree values, you'll see for graph G, right, it has 2 vertices of degree 3, that's A and E, and it has 3 vertices of degree 4. And likewise K has the same thing, it has 2 vertices of degree 3, that's L and M, and it has 3 vertices of degree 4. So again, they are the same, right? Now, if these 3 things happen to be the same, then there's a good chance that the 2 graphs, but not necessarily, are the 2 graphs isomorphic. But once I've done that, what I'm going to do is I'm going to set about seeing, is there an isomorphism, and if there is, then what is it? So here I've redrawn the 2 graphs G and K. Now we're going to set up an isomorphism that links the vertices in G with the vertices in K. Now the vertices will be linked to each other or be similar to each other if they have the same degree. Now if you look at the first one up here in the degree table, the degree of A is 3, the degree of L is 3 also. So let's have a look, and let's say that L, if I rename L as A, right? Now looking at the positioning, I can rename P, which has degree 4, as C. I can rename N as E, and rename O as D. And the one here in the center, I can rename that as B. Okay, so you can essentially see by me doing that is that the 2 graphs are isomorphic. So let me write that down. G and K, you can see, are identical. So they are isomorphic. Okay, they are isomorphic, and the isomorphism, right? Let's call it I, right? What it does is it maps, right, G onto K in such a way that the image of, let's say, the point A under the isomorphism I is equal to L, right? The image of the of the point B under the isomorphism I is equal to M, right? The image, and I'll go to the next line, of C is equal to P. The image of D is equal to O, And lastly, the image of E is equal to N. So to recap on this, two graphs are isomorphic if they're essentially identical to each other. They may be drawn and labelled in different ways, but essentially they're the same structure. So if I move up here just to recap for you, I would do out this table. I think it would be very helpful in this sort of question to check if two graphs are isomorphic or not. I would do out this table. And I would check the number of vertices, number of edges, and the degrees of each vertex or of each vertice in the graph. And check if they are the same for both graphs. If they're not the same for both graphs, then automatically you can conclude that the graphs are not isomorphic. If they are the same for both graphs, you can set about looking for the isomorphism. So in my case here, what I did was I redrew the two graphs, and I then set about looking for the mapping that mapped one graph onto the other, and I came up with this. Okay, now let's look at part G. Here I'm asked to draw K3, K4, K13 and K24. These graphs are specific graphs in graph theory, and all I want you to be able to do is to show me the structure of them. So first let me look at K3. The 3 indicates that there are 3 vertices in the graph, so let me just draw them in. There's 3 vertices. And this K graph indicates that every vertex is connected to every other vertex. So this is connected to these two, and these is connected to these two. So K3 has this structure here, triangular structure. If I look at K4, the 4 indicates that it has 4 vertices, so 1, 2, 3, 4, right? And again, the K is that every vertex is connected to every other vertex. So let me connect this one first to every other vertex. All right. Let me do the same for this one. And lastly, let me do the same for this one. So there's my K4 graph. If I do now out K13, well, here I have 2 sets of vertices. I have one set that has just 1 vertex and another 3 here. So there's 4 vertices altogether in the graph. But what it tells me is that this vertex here, the 1, is connected to all the other 3 vertices. So that's what a K13 graph looks like. And lastly, a K24 graph, again, the 2 points here, right, is one part of the graph, and then I have 4 points over here forming another part, and all these 2 points are connected to all these other 4 points. 1, 2, 3, 4. And likewise, this point is connected to all these 4 also. 1, 2, 3, 4. So that's K24.